Hey chemistry students, this is Mr. Ferguson. We're here to introduce Unit 10 of chemistry, where we take a look at the behavior of gases and the gas laws. So for lesson 10.1, we're going to introduce the unit and go over the properties of gases. We'll compare the properties of gases to the properties of the solid and liquid states of matter. We're going to introduce you to this thing called the kinetic molecular theory, which we use to explain the properties and behaviors of matter in different states. And finally, we're going to compare a real gas to this imaginary gas that we talk about in chemistry a lot of the time, called an ideal gas. So let's get started. When we describe the behavior of matter, our explanation for why matter does what it does in each state is based on something called the kinetic molecular theory, which makes some certain assumptions about what is going on with the particles that matter is made of.
It usually deals with ideal gases as well, I think.
Ideal gases have
assumes
some
ideal gases, I think.
But how do we explain why solids act the way they do, why liquids act the way they do, why gases act the way they do? It's based on this theory that we're about to cover, and there's three primary assumptions of this theory.
And the first assumption is that matter is composed of tiny particles in constant, random, straight-line motion. That is something you have to know, that if a gas is moving, it's moving in a straight line, assuming no outside forces, of course.
Right, so it's still following the Newton's laws of motion. That is, in the absence of an external force, an object's going to continue at a constant velocity.
All right.
The second assumption of this then is that this particle motion is constantly being interrupted by collisions. So the collisions could be between the one particle smacking into another particle that they happen to, their trajectories intersect and they bop into each other, or the particles could be colliding with the surfaces, say, of a container or of anything that they encounter. So this is like a picture, one of those lottery machines filled with ping pong balls, and they're about to draw. The balls are just constantly jostling around. So that's the second assumption.
With that, actually, those collisions are actually how most particles transfer energy from one another.
Right.
But that's a different point at a different time. The third assumption here is the velocity of particles is greater at higher temperatures and lower at lower temperatures.
So when the temperature gets colder, the particles slow down, they have less energy, the collisions are less energetic, less energy transfer. At higher temperatures, the reverse.
Yeah, this is why the absolute zero means there is no molecular motion, because, well, it made it so cold they stopped.
So those are the primary assumptions. Now let's go kind of take a look at the three states of matter and what comes out of this kinetic molecular theory and how we explain the different properties of matter states.
So here we are looking at a chart of different properties of different states of matter. We're going to look at the shape, volume, the mixing, as in do they mix in well with each other when they move around, and also the particle model, what they look like on a molecular view of solid, liquid, and gases. So first off, we have a solid, and the shape of any solid is definite. Think about anything that's solid, like let's just say a quarter, for example. You take a quarter, you drop the quarter in water, it still looks like a quarter. Next, you have the volume. Regardless of where you put this quarter, put it into a beaker, put it on a tabletop, put it up in the air by throwing it, it remains the same volume. It doesn't change its volume.
So another way of expressing that is to say that solids are not compressible.
No, they're not compressible.
We'll get into why that is when we do the particle
expandable.
model. Right, they're not compressible or expandable. And as far as mixing goes,
If I put one quarter next to another quarter and flick them into each other, you don't make one larger quarter, they just collide. And this has to do with how the particles are moving. They are not open to being put with other particles.
so let's kind of represent what's going on with the particles in the solid. So we can draw a little grouping of particles very close to each other. And
These particles that he's drawing, They have freedom of movement in that they can move in all directions around them, but since they are not able to escape from one another, they are constantly hitting into each other and basically just vibrating in place. So solids do move, there is molecular motion, but they are basically just kind of vibrating in place back and forth, up and down, left, right, whatever you want to think, but they're not able to escape each other. All right.
And so, which would explain the fact that their shape's definite, because their particles are kind of locked into a certain grid-like arrangement. It would explain the fact that they don't expand or shrink, because they just are, again, at a sort of a fixed distance from each other, a fixed arrangement, and they're not going to mix with other things because they're kind of locked together in this little grouping. And if another grouping of solid comes next to them, they just stay in their own little unit.
All right, the next kind of state of matter is liquid, in which the shape of any liquid is indefinite, because if I have a glass of water that I pour on top of a tabletop, it'll take the shape of the tabletop. Or if I have a glass of water that I pour into a beaker, it'll take the shape of the beaker. It just means that it takes the shape of the thing that you put it into. The volume, on the other hand, if I have 100 milliliters of water and I transfer it from one beaker to another, it's still 100 milliliters. So it's a definite volume. It does not take the volume of the container. As for mixing, we all know this quite well. If we mix two liquids together, assuming they have similar polarity, they will mix together. So they do mix. Of course, like I said, unless they're different polarity, like oil and water.
Oil and water
then they
won't,
separate.
but if their polarity, as long as their polarities are good, compatible, that they can readily mix with each other.
And the particle model of this is a little more difficult to think of. They do move in straight lines still, technically, but now they are more sliding around each other, where they have more freedom of movement, but they are still contained into a certain amount of space. So they move around each other.
Extremely close to one another. So I'm drawing little particles, and then the little arrow would represent the random direction of their motion.
This is difficult to draw compared to a gas, so we're going to try to make gases it's noticeably different than this. All right, for gases now, we're done with liquids.
Mr. Ferguson.
1 second. All right, so the last state of matter is gas. Think about any kind of gas that we have. The shape of a gas is indefinite. It'll take the shape of its container. It's hard to show because most gases, of course, are colorless.
Invisible.
Makes it difficult to see. And then the volume, of course, is also indefinite for a gas. I can take, a 10-liter volume of gas, and I can put it in a 50-liter volume vessel, and it'll still fill up that vessel. Now, the thing that changes is the pressure, but that's, again, a later concept in this unit. As for mixing, pretty much every gas will mix with any gas. I'm sure there's an exception somewhere, but to my knowledge, all gases mix.
And they mix very easily with, you don't even have to stir them. They'll just mix up on their own.
And then comparatively, the particle model for this is there's a lot of space between each particle. They're moving in straight lines. Now, granted, these things still undergo tens of thousands of collisions a second.
There's one colliding right there.
There you go. But it's just, they collide a lot of time, but compared to liquids and solids, gases have a large volume of space between them.
So I'm going to say two things that are different between the gas and liquid. One, they have much higher particle velocity.
More energy, more velocity.
And they have much more space between the particles. So they're much further apart than which would explain why, when we come back over here, gases can be compressed a lot. You can take enough gas to fill hundreds of balloons and compress it into a very small canister, and then allow it to escape, and it'll expand back to to a much larger volume. So, as we discuss gases, which is our primary focus, we're going to keep throwing this word out there, the term an ideal gas. And there is actually no real-world gas that is truly an ideal gas.
There are
but
ones that are close.
There's
but
some
not...
close ones, but it's an imaginary type of gas which we've constructed, and it behaves according to two primary assumptions. Okay, so we've got the assumption. You're going to want to write these down because this is important. One, in an ideal gas, there's zero attraction between the particles. They have no desire to stick to one another or repel away from one another. They are kind of neutral towards any other particle.
Like bouncy balls being hit off of each other.
Like a bouncy ball.
Number two is that molecules are points in space and have zero volume. So
the volume of an ideal gas is determined by the collisions and the spacing between the particles, not by any volume that the particles occupy themselves.
Now, in the real world, as all gases behave this way, molecules take up a small amount of space, and there can be an attraction between the molecules. These are usually van der Waals attractions, but you can have different types of attractions, polar, dipole, stuff like that. However, most real gases behave much like ideal gases under most conditions. What does this mean? That means we have some examples, like if we have an extremely cold environment, so if it's extremely cold, if you start getting close to the freezing point of a gas, it will start to turn into a solid or a liquid. Or if you have extremely high pressure, if you compress these particles so much that they start hitting each other very rapidly, you will turn it into a liquid. So that's why these gases will stop behaving ideally if you have an extremely high pressure or an extremely low temperature. So that's just something you have to keep in mind. Most gases act ideally under standard conditions, but when you start getting them at high pressures or very cold, they turn into liquids or solids. This is how we make liquid nitrogen. So if you remember those demos we did back in probably February now, that nitrogen liquid was made by actually compressing nitrogen gas. They just took a big old compressor,
and cooling it.
Just by compressing it, they turn it into a liquid. So it was completely.
You squeeze them close enough, then they start to stick to each other and make a liquid.
There you have it.
Okay.
All right, that's all for today.
All right. See you soon.